It's my pleasure to present Bianca Dittrich, who is a faculty, she's faculty chair, as far as I know, at the Perimeter Institute for Theoretical Physics in Waterloo. Yeah? Bianca is known for her work in loop quantum gravity and the spin foam approach to quantum gravity. She's been at the Perimeter Institute since 2012, but she was prior to that a postdoc at the Perimeter Institute for, I think, 3 years, you said. She received her PhD in 2005 at the Max Planck Institute for Gravitational Physics in Potsdam, which is just outside of Berlin. And in 2005, under the direction of Thomas Tiemann, yes. And then she was a Marie Curie Fellow at, not then she was a postdoc at Perimeter, then a Marie Curie Fellow at Utrecht, and then has been appointed at the Perimeter Institute as faculty, and where she is faculty chair. She's made important contributions to loop quantum gravity. Her most cited papers, now I looked this up, partial and complete observables for canonical general relativity. Okay, of course, Bianca is the recipient of the 2024 CRM CAP Medal for Theoretical and Mathematical Physics, and this is why she's giving this talk. So please, Bianca, go ahead.
Thank you for the introduction. So, as Manu mentioned, I'm working on quantum gravity, and so my aim is to describe two aspects of the theory and of difficulties you encounter. Unfortunately, will not be explaining quantum gravity, which would be a little bit much, but let's see. So, quantum gravity, we try to unify quantum field theory and general relativity for a number of reasons. One is that both theories are somewhat incomplete, and we hope that quantum gravity will give us a more unified and better description. Now, according to Einstein, gravity is not so much another force, but it's actually encoded in the quantum spacetime. And so that means constructing a theory of quantum gravity, you expect to obtain a theory of quantum spacetime. So new notions of space and time, which would be quantum. We can make some simple deduction experiments that indeed we might have to expect that if you try to combine quantum field theory and gravity. And so typically these involve black holes. So in this case, if you want to resolve two space-time points which are very, very near together, you have to concentrate lots of energy and go to very short wavelengths to resolve these points. That means that you concentrate a lot of energy in the very small regions. And so then there's kind of existence theorems by Penrose and Hawking, which say that generically you form black holes. Yes.
What does it mean to resolve 2 points?
That's a good question, but
Transfer energy?
optically, you would say if you could see 2 events which are very near together, then they are really 2 separate events. And the usual, and take it as the usual meaning of this loop.
Wavelength is huge.
And so, in principle, we have manifolds where we assume that we have, in principle, the power for infinite resolution. But this doesn't seem to be the case. That's the entire point of the story. So there seems to be a bound on the resolution. So, and if you believe in these kind of arguments, very similar to the Heidegger uncertainty principle, that implies we need to really change the classical notion of space and time. So there might be something different, really describing space-time. One possibility to approach that, and that was probably one of the first approaches to quantum gravity, is so-called canonical quantization. We need to take a so-called observable algebra describing geometry and quantizing this geometry. to quantizing these observables. This gives something which I will call quantum geometry kinematics. So I will make this difference for a number of reasons. One of these you will see. And you can understand that kinematics and the kind of question to answer the first question, to answer this question, can we expect smooth manifolds to emerge in a continuum limit? So already this question turned out to be very difficult to answer, or the problem was that people tried a variety of quantum gravity approaches, and what they got as a continuum limit was not even a smooth manifold. So it's already a non-trivial question. And so if you have canonical quantization means usually you start with initial values from the initial value hypothesis embedded in your four-dimensional space-time. And so for gravity, the initial values are the spatial metric and the extrinsic curvature. And they are kind of canonically conjugated to each other. So in principle, we have these classical observables or k-space variables.
You have to.
Yes.
Is there a stick?
There's no stick.
So you have these space-based variables. Well, what quantization means in the first naive sense is put tags on it, which means we have to find a Hilbert space which carries a representation of these observables. So we would like to have a Hilbert space and have these the space functions represented as operators and reproduce basically the commutation relations there. And this has been tried in a number of ways, but the issue was that one couldn't find a nice Hilbert space description or representation which would be carrying or which would allow for a representation of just the spatial diffeomorphisms. And one reason for this is the following. So here we have these point-dependent operators, also just in quantum field theory. You have these point-dependent operators, which are not operators, but operator-only distributions. So if you're more mathematically inclined, you smear them over three-dimensional space with some test functions. And only these objects are well defined. So that is an important aspect. However, the resulting object here, which is just the integral over space in this case, is actually not invariant under diffeomorphisms, because here you have just scalars. What you would need is a scalar density. So something like the determinant, the square root of the determinant of D of the matrix. But then you would get something which is space dependent on the right hand side. So that is kind of a key issue. If you work with these kind of point-dependent operators or operator distributions. And so this was nicely resolved more as a byproduct than as intentionally by the introduction of new variables. And so that goes back first, there was Sen, and then Ashtika really put down the phase-space theory for these variables. And back then it was, people were very hopeful because the Newtonian expressed in these new variables was polynomial. Now this is again not an important aspect of the theory anymore. But the important aspect is that you could formulate a GR in these variables which are a connection and basically an electrical flux. So this is very similar to the electrical field, just that these are algebra valued. And they encode the extrinsic curvature and the symmetric. And these are the same variables you would have in Yang-Mills theory. Or also, actually, what turns out to be more important, there's a topological theory, the F theory, which also has the same variables. Okay, yeah, so topological VF. Okay. And what's it? So connection is a one form, so you can actually naturally, you should naturally smear it over one-dimensional objects. In effect, what you should form is a holonomy. And so an important aspect here is also that the holonomy is the exponential of the connection. And so mathematically, connection is Lie algebra valued. It's a SU2 Lie algebra, so it's non-compact. The holonomies are root valued, SU2 root valued. These are compact. And that plays a very important role for making the Hilbert space construction possible and for getting the results like discrete spectrum. And so this you can you naturally can integrate over the curve. So this is also a one form, but then you can do a watch tool, and you kind of can naturally then integrate it over two surfaces and basically measure the electrical flux or spatial geometry. And so this is one dimension, this is two dimension. So in the end, if you consider the Poisson brackets or the commutator between these two observables, instead of a delta function or of a three-dimensional integral, what you get here is just something, a constant. And so you get a homologation relation, which is topological, in fact, that's from a topological field theory. So, I mean, it's more complicated than one. But if you get some non-vanishing results, if the curve for this holonomy cuts the surface, and you get zero if it does not. And also this result basically is actually this is other thing is actually diffeomorphism Cohen, and it does not involve any Deacon matrix explicitly.
What is your bracket?
Well, this is actually, you can define them classically, then these are
Poisson brackets.
And operators, this will be also the commutation relation in the Hilbert space. Okay. So this is variables, this is observables, we fix these observables, and you can allow any curve here and any surfaces here. So that is important in the context of constructing a continuum Hilbert space. And how you construct one way to construct a Hilbert space is you have to choose a vacuum, and then you apply all operators to this vacuum, and you generate a Hilbert space. You also get an Neumann-Ziegler construction. But the important point here then is that you have to choose a vacuum. And well, the entire talk was really about whether the vacuum is unique or not. The vacuum which was chosen originally, I don't know if it was chosen, was for a long time, or was it's a only choice, is basically defined as a state that is annihilated by all electrical flux operators. And so if you do apply electrical flux operators to the state, you get zero, of course. However, if you do apply the conjugated operators there, you get something non-vanishing, and that would generate excitations. And so you can have a mnemonic device, which is, okay, so here you have basically the vacuum. And here you basically have all these curves which come from these holonomy operators. Where the holonomies are good value to make sense of them, you have actually to take some representation labels and some indices, so I leave these out, but here it's still the representation labels. And that roughly gives you a spin network if you have got this expression.
Holonomies are always closed curves. Yeah.
Here you can also take open curves, but then you have to put some intertwiners if you want to make big generators. Okay. There's a lot of additional formalism which I have to skip here. So there's an inductive Hilbert space formalism and an inductive limit for the Hilbert spaces. To construct this inductive limit, we have to ensure a lot of consistency conditions. And it was the first rigorous realization of quantum geometry. So if you read quantum gravity textbooks, that's what this always emphasized. And are supposed to, like these so-called EDM variables, give a spatial matrix and the extensive curvature, and this was not possible. And this method, well, it's a GNS construction, it's a very general construction, and it also tries to standard quantum field theory, where we know it does Fock space, basically. But let me emphasize that this construct, that this resulting Hilbert space and the Fock space are very different. The Fock space is, well, the Fock space vacuum is defined as a state which is annihilated by all the annihilation operators. And the annihilation operators are not like either field operators and conjugated momenta, it's a holomorphic combination, which means that you get Gaussian states with correlation, there is fluctuations and so on. But these fluctuations, you know, they have information on the background matrix. It is a flat matrix. So that's why people tried, but it was not possible to get any kind of Gaussian-like states as a vacuum. So here we have a state which is sharply annihilated by just flux operators. So it would be like having a vacuum state which is just annihilated by the position operators. So that is a big difference here. And so we don't expect that this is a vacuum state of quantum gravity, which basically is an open question what it actually is. But just to say that this is a particular vacuum, because if you remember, I said all the electrical fluxes, they encode the spatial geometry. So they measure areas in your hypersurface and sea volumes and so on. But they are always zero. So the vacuum state is sharply peaked on the state where all spatial geometry is zero. It's totally degenerate. There's zero volume, zero area, and so on. So if you generate a more complicated state, here you see like a graph state and so on, you can have a huge gap. It doesn't mean anything that this is a big area in the way I go through here. So this means that here really you would have no geometries. And so here we have only kind of non-vanishing geometries along these edges and nodes of your graph. And so here you see how this quantum state, you have these graphs, you have these spin representations, there's a spin representation leading these graphs. These would tell you what are the areas and then also angles and volumes and so on, which you could measure in the state. So the quantum states determine quantum geometry. Okay, and one famous result is that about the spectra of geometric observables. So this means observables in particular that you can build from the electric flux. And one observable you can build from is the area of the surface. There's a simple rule in quantum mechanics, basically. If your conjugated observable is compact or lives in a compact space, then you can expect a discrete spectrum. And so here it plays a big role that we have these anomalies which live in a compact space. And so these electrical fluxes or the areas rather give you discrete spectra. And also non-commutative because this is actually curved space. And these generate like they behave like derivatives on this curved space, so you get actually non-commutative derivatives. And so this is the result that area operators have a discrete spectrum. So there's the smallest area, there's also states with zero area. So this was always hoped to be acting as a UV cutoff. But areas can be still super large. So you know, again, it's not how your state looks like, but what really are the labels. So you can still have an infinitely, I mean, your spin number can be arbitrarily large. Even say also surrounding areas that are really small. Okay, and so this result comes really from having these exponentiated connections. So mathematically, the Holomies operators exist, but they are kind of not deeply continuous, so the connection is not very defined. So these representations were constructed in the 90s, and around 2006, there was a uniqueness theorem known under this acronym LOST or F-LOST for all these gentlemen up there. And so basically, it started with a number of conditions. And so it's kind of, if you want to have a representation of your observables which you want to represent, the Holomies and electrical flux operators, and you will want to have spatial diffeomorphisms acting as automorphisms and so on. But there's only one choice. And that was this Ashley-Lewandowski determination. And that was celebrated very much because people say, look, there's only one diffeomorphism invariant possibility, or diffeomorphism. But one possibility to construct a quantum geometry, it would be nice with respect to spatial diffeomorphisms. And we have the right one. So. But there's an issue because the vacuum state is where I have no geometry. And what we are at some point in that, what you should always do as the first test is to show that you actually have a reasonable semi-classical limit. As I say, it's this non-trivial task of showing that we actually get like smooth manifolds and something which approximates flat space, so our universe, in some sense of semi-classical limit. And what you also wanted to have is at some point, in fact, propagating degrees of freedom. And so if you look at statistical physics, then these such continuum limiter or such continuum limits appear at higher order phase transitions. And phase transitions are kind of transitions between different vectors. Here, however, it's a claim that we only have one vacuum. So, could there be different vector? And the answer is yes. So there was a uniqueness theorem, so we had to kind of circumvent the uniqueness theorem. And it turned out what you had to do was to slightly change the algebra of observables, or actually the observables you choose to represent. But then it turned out there's actually a general principle, namely to use the topological field series with defects, which of course should carry all the notion of diffeomorphism with it for the construction of these quantum geometry representations. And one example are the F-series. The F-series have an action, okay, B wedge F. So F is a curvature, and V acts as a Lagrange multiplier for the curvature. So we describe these spaces with vanishing curvature. And so instead of having vanishing spatial geometry, you could have states with vanishing curvature. Another possibility is even to go to higher gauge theories, which I think I will not comment much here. And so one thing you can try is to kind of define something which would be basically the dual vacuum, so that everything would be dualized with respect to the first construction. So I will leave many details out, but instead of choosing a state where all fluxes vanish, you choose a vacuum to be the state where curvature vanishes. So all holonomies give you unity. What you then have to do, I mentioned that it's important that like the holonomies are valued in a compact space for technical reasons. So here now it's important that the fluxes are valued in a compact space. So what you can only represent are exponential fluxes, Toft operators, and these give you excited states with curvature defects. So now we have a new non-negative vacuum state, which now describes basically the completely different state of the first phase. And you have things which are excited by your Toft operators. And so they will be labeled by surfaces. So we have a system of surfaces. And these labels which come from these choices of exponentiation. Now, as I mentioned, basically we avoided the uniqueness theorem, because the uniqueness theorem does require that the electrical fluxes exist as operators. And here they do not exist as operators. So these operators in alpha are not weakly continuous. You can play this game also with just square integrable functions of x. So if you have x and p, you all know the standard Schrödinger representation. But there's basically also some theorem which says, oh, this is a unique construction. But in fact, if you allow only exponential IP to exist or exponential IX to exist as non-weakly continuous families of operators, then you get a different representation, you get a different Hilbert space. Yes. So we have now this new vacuum state where curvature vanishes. Like all the spatial geometry is maximally uncertain. And if you try to express that, this state does not live in the previous Hilbert space. That's two different elements. So if you want to express it with respect to the previous or approximated by in the previous Hilbert space, that would be a really highly excited state with respect to the old vacuum. So principally you can easily describe here large scale geometries. 2 + 1 dimensional gravity, so gravity in 3 dimensions. Equation of motion happen to say that these are flat, so this vacuum state would be actually the physical state of 3D gravity. And that would be the new representation. You can also define new excitations and a new basis and so on, and all these things we have basically constructed in various papers. And there's a disadvantage here, which is that we lose certain finiteness properties in a subtle way. So what we actually did is indeed a Bohr compactification of this of the Lie algebra. And this is a somewhat brutal way to do things. First of all, it does introduce these parameters alpha. And also leads to funny things. If we now look at the area spectra, or actually areas is a spectrum of the area square operator. When they're mostly mathematically speaking, not discrete, but continuous, and the eigenstates are actually not normalizable, but they do look discrete. So the non-discrete response from having these curves oscillating infinitely, and basically in the end you get a continuous spectrum. So it's
What is this Bohr compactification?
it's technically just you end one point at infinity, but what it also means is basically each point, the topology is that each point is a complex set in itself. So, environment in itself.
And Niels Bohr did this?
No, I believe it was
Some other Bohr, okay.
and it appears in this, as I mentioned, in these funny representations of x and p, even if you only allow exponential ip to exist, or exponential ix to exist, then what you get is instead of L2R, you get something like the square integral function on the Bohr compactified space of R. Okay. Can we do better than this funny thing, like the Bohr compactification? And yes, the answer is yes. Actually, there is a topological quantum field theory. I mentioned that you should use topological quantum field theory, known as view, which happens to actually describe 3D gravity with a positive cosmological constant. And this describes homogeneously curved geometry. And so, indeed, in that case, you are in a situation with very high symmetry. Your holonomies are SE2 valued, and your momenta are also SE2 valued. So I'm simplifying a lot because in the end you get a quantum loop structure, and this is a somewhat complicated object. Here you get some kind of double finiteness, and in fact, you are kind of UV and infrared finite, and you have discrete and bounded spectra for all geometric observables. So also you cannot have arbitrarily large areas anymore. Naively, you cannot have arbitrarily large areas because all the areas, all the surfaces you have to imagine homogeneously curved. So on a sphere, you cannot put on a sphere of a given curvature, you cannot put an arbitrarily large area without getting into covering itself and so on. So that is a basically the cutoff. So this is more natural, but and importantly gives you UV and infrared finiteness, so a smallest area and the largest area. But then what about 4 dimensions, 3+1? And the technical difficulty here was that in this 2-0 TQ3, so also your electrical fluxes, they're homogeneous, they're now living in a curved space, which means your holonomies become non-commutable. And 2D space means that if you draw one edge over another edge is different from the other way around. But this is a notion which you can have in 2D. In 3D, it's not very clear what is the first holonomy, what is the second holonomy. So the question was how to generalize that to 3 dimensions. And here we invented a technique to take a topological quantum field series in 2+1 dimensions and lifted them to kind of state spaces for 3+1 dimensional series. And for that aim, we kind of combined with something in topology known as Hilliard splitting. So you can represent a 3D manifold by a decorated surface, so by a 2D object. And this decorated surface is the surface of a skeleton, which is a bit arbitrary. You can choose. So in this example, you take this triangulation. It's actually a 4 simplex. If you take the boundary of a 4 simplex, that is a C-sphere. So the boundary of a 4 simplex represents the triangulation of the C-sphere. And so you blow up the edges a bit, and the vertices to little balls and so on. And then you do obtain the surface of the blown up triangulation. And that defines it as a Hegel surface. And together with information on what are the contractible and non-contractible curves here, this encodes you completely the topology of your 3D manifold. And so we basically define these, takes a 2+1 TQFT states, define them on the decorated surface, but interpret them then as 3+1 states. And that allows us to indeed define quantum states for 3+1 dimensional quantum geometry. And in this case, if we fix the skeleton would be basically the objects where excitations can sit on. This simple space would be finite dimensional. We want to then go to the continuum limit, we have to define, and you would get to infinite dimensions. If you restrict to a fixed skeleton, you would be finite dimensional. And again, here you have a high level of symmetry. All operators would be some kind of Wilson loops, but the Wilson loops mean something different, whether you go around these contractible or non-contractible loops here. So this would be A or B cycles. So here you would say this is contractible loop in the surrounding manifold, and here you go around the skeleton itself. That's when you could have curvature sitting, so this is non-contractible. And you can either diagonalize one set of Wilson loops or the other set. And that gives you different kinds of bases and so on. That gives you discrete and finite spectra for all geometric operators, so for the area and curvature operators. Hence to be the same spectrum. So this indeed describes nicely homogeneously curved geometries, so which you expect to appear here in cosmological constant. So geometries which are piecewise homogeneously curved. So if you use them together, you have much more. If you use these pieces together, you have much more freedom to get a general states which have more general curvature.
Okay, what are these parameters? LP and lambda?
Yeah, sorry. So capital lambda would be the cosmological constant, which would induce, where the vacuum state would be having some homogeneous curvature, and LP squared is just the Planck length squared. And that is this funny K is this K that would be the level of S2, which appears there for the quantum group, and appears here in these spectra. And here these would be the various representation labels you have for either the appearing in the state or in the Wilson loop operator. Yes.
At this stage, there is no small structure, right?
I mean here, yeah. So here we have previously seen that through this construction of saying we have a vacuum state and then we apply these operators. But these operators, for instance, are based on curves. So then your state lives on this drawing all possible curves. So you typically get states concentrated on graphs. So here, similarly, what we get is states based on these skeletons. So these look discrete. In principle, you can make a construction, which is this inductive limit Hilbert space construction, which I haven't commented on, to have a continuum limit, but at each level, the state would look like this state has would be based, or all the excitations would be based on these discrete structures.
So what's the curvature of this?
What is the curvature of this state?
Yes, what
What is it? So curvature would be you would measure it with an operator. In this case, you would measure it with operation loop. And the possible outcomes are encoded in the spectrum of this Wilson loop. And so here it basically then this is bounded because you have lots of sine functions. And for some reason this can be not zero. So you get you get some results like only curvature, but also like you can also not have arbitrary small curvature or arbitrary small area. You can have zero area and zero curvature, but not arbitrary small.
But just last, I mean, I didn't see you add any dynamics. I did not see,
Speak about dynamics,
Yeah,
yes. So
but these parameters, I mean, LP comes from, you know, Einstein action over G or something like that, or lambda.
yeah.
I mean,
Yeah, so this is a choice. You choose that you can have different vacuum state with different choices of these parameters. I mean, this has to be an integer. Well, H bar, you know, in the LP is H bar and G there, but G comes classically and H bar by the quantization. This is indeed a choice. So just that there are different, you know, so in fact, these states which I constructed would indeed appear in something known as Crane eta TQFT, but with defects. You know, Crane eta TQFT would be, well, have a label, you have to make a choice for the level of SU2. Also, here in condensed matter for Stiglitz one-dimensional topological quantum field series. And it's known as Walker-Wong, which have only defined these things for a specific choice of the skeleton for the cubic lattice. Anyway, this trick, which was kind of combining, I don't know if you want algebra and topology, it was also the first time we implemented this quantum group structure into 3+1D. The main technical difficulty is indeed to have this non-commutativity of Wilson loops and for the three-dimensional space. And if you restrict to these fixed skeletons, your Hilbert spaces are finite dimensional. And that's just very important if you want to go to the dynamics and show that you have hope to get to find, for instance, phase transitions and so on. Or how does it help for the dynamics of quantum gravity? So we have now the situation we've gone from there's only one unique vacuum state. Unfortunately, it's a very inconvenient vacuum state, which describes only totally degenerate geometry. Where there are many vacuum, again, these are kinematical, and those realizations for your quantum geometry. And as I mentioned, statistical physics or insistent, these vacuum correspond to different phases. So one way to implement the dynamic require path integral and spin form amplitudes. And then you would be interested in, like, if you treat the spin forms as a statistical system and look at this continuum limit and include lots of building blocks and in the continuum limit, what is the phase diagram for your system? And so statistically, you would expect an interesting continuum limit at higher order phase transitions, and now these you have prospects of having lots of phase solutions. And we tested this principle in lower dimensional systems because the dynamics of spin forms, well, in 4 dimensions is really complicated, so we are building up to that. Okay. No, I have basically 3 slides left to say something about the dynamics, but it would be quite a change of topics. So this was kind of the more mathematical part, because I actually have not talked about lots of these mathematical details. But this is about the construction of lots of individual states. So, it was hoped that you can indeed construct a continuum limit, they get smooth manifolds. But assuming that we get this, can we expect to obtain also the dynamics of GR? And so that's what I wanted to shortly talk about. And so that's more a dynamics question. And let me just tell you what the problem was. So we have seen that we had area operators and they had a discrete spectrum. And also it's for larger spins, for larger areas, it's still asymptotically equidistant. So areas are much more fundamental than lengths, as we will see. But in a discrete triangulation, you have far more triangles, and so therefore area variables than edges, and therefore length variables. So in fact, in this construction of the dynamics or dynamical amplitudes, what you should do is to impose constraints on these area variables, so that you can obtain convolutions which do allow for consistent length assignment. However, if your areas have discrete spectra, these constraints will be Diophantine equations, and they cannot be imposed sharply. Actually, there's really that the first class algebra, constraint algebra turns into a second class constraint algebra. So there's an anomaly, and implicitly what people did is to impose these constraints only weakly, and then have not thought about it. But then what happened is that people argued, oh, if I try to do a significant limit, what seems to emerge is that all geometries seem to be restricted to be flat. And so that was known as the flatness problem of spin forms. And the thing you don't see is like it started in 2008 with a paper by Valentin Monzon. And then, for more than 10 years, people argued about whether it is actually whether spin forms are doomed in this way or not. And so one issue why this was an open question for such a long time is that you have all these nice topological construction tools, but they lead to highly complicated amplitudes. So even for just one simplex, you need really high performance computing, which there's algorithms which were developed over 5-6 years with a great effort. Compute amplitudes for very small triangulations and even small spinning. And so this is about the dynamics, is that just like in QCD, you put it on a computer, but it's much more complicated than QCD's amplitudes. And so we came up with effective spin forms, which capture key principles of spin forms and are based on higher gauge theory and turn out to be much simpler. Also, higher gauge theory sounds a bit scary, and that happened to be give you a much more transparent encoding of the dynamics. In particular, we could just calculate things on a laptop instead of HPC, and so we could indeed test the equation, the discrete equation of motion on a simple triangulation. And it was showing that actually one can get curvature. So the flattest problem was resolved in this case of having very few building blocks. And this calculation is actually still not reproduced by other models. So I don't know what the result is, but still this calculation has not been reproduced. And we have none of them independent. So still a couple of this. Just shows you what the complexity is. But then there was a question, what about the case of many building blocks? Again, since we had a very transparent encoding, what we could consider is a perturbative large scale limit on a regular lattice. So take this lattice to be of this infinite many of these cubes, hypercubes, with 4D. And so actually the results were very surprising. But actually I started this in order to possibly show that spin proofs cannot deliver gravitons. So I found the opposite result. So basically, the results were that at leading order, so this is perturbative, you do get a linearized Einstein-Hilbert action. There is a next order correction, which is even coming from the fact that the areas are more fundamental, and that is a y-squared term. And these constraints I mentioned in the beginning, whether you oppose them or not, doesn't seem to be even important. And that is an important point because there's a couple of spin-form models and they differ in the details of how to impose these constraints. But as often happens in the continuum method model, there's a kind of universality kicking in, which tells us that this is not super important. And so actually, what we considered here was a continuum limit of a system of an action, the Eigenvector action, where people thought for a long time that it could not lead to GR, but nobody ever checked explicitly. But then the pandemic came, and I thought we had nothing to do, so we could do that. Moreover, one can basically find confirmation of these results. And the continuum, what spin forms are based on is a Klebanski action. I'm not going to explain what it is. You can ask me otherwise. And there's a so-called modified Klebanski action, which exactly captures this effect which I was saying, that instead of strongly imposing the constraints, you impose them weakly. And so what we had to find is a subset of constraints to do that. And what we in the end put right down is an action which reproduces this lattice result and looks, if you integrate out the additional area variables which are not lengths, and you get just an effective length action, then you get this non-local action. And this Einstein-Hilbert and y-squared divided by this funny non-local term. So that brings me to the end. Just to summarize that, I was speaking about quantum geometry kinematics, which indeed was kinematical. There was not much dynamics. But this was the question, can we have different Wegener states, in particular Wegener states, which would be a more convenient starting point for the dynamics? And for answering questions like would there be phase transitions in interesting continuum physics? Well, I mentioned that for the full models, it's really hard to even compute the amplitudes for one building block. So you can imagine that it's really hard to compute the amplitude to answer what is the statistical phase for four-dimensional triangulation with many building blocks. So even for condensed matter models, which are much simpler, it's hard to investigate that for much simpler models like the Ising model. So we are developing develop tools which in lower dimensions, and that would be 3D. Like tensor network techniques and so on. But it's in general a hard question for many approaches. And I spoke shortly about quantum geometry dynamics. We did take a bit of a shortcut, but where one could show if you can address this very if it's a non-perturbative question of defining a state where you get a smooth or something like a smooth manifold with flat space, you do get the right dynamics on top of that.
Thank you. Thank you very much, Bianca. Are there any questions? Well, John.
There I am. Is there an experiment with the result that is explained by good quantum gravity that can be otherwise explained?
So that cannot be otherwise explained. I would have to check. So there's a number of proposals which come from loop cosmology about the CMB spectrum, and whether it's mutated and so on, but I cannot tell you spontaneously whether there's other theories also depicting that. Also cosmology, there's lots of more debate. So I cannot tell you whether that is unique. Here I have this little corner, which might be more unique, or I would say it seems to be more specific to series which are based on an area metric, which seems to come out here. So indeed, that seems to be an important feature of loop gravity, is that area variables are more fundamental than lengths. So instead of a length metric, we have actually this area metric. Area metric in 4 dimensions has, for instance, 20 components instead of 10 components.
What is the quantity that is observed or measured?
Yeah, so they asked for poor GR if you write action terms, if your modus minima and action terms. For pure GR, you cannot write anything which is parity breaking, but for the area metric you can. So there could be parity breaking effects. One example we have seen is that, for instance, in this dynamics, what you get is a mixing of the plus and cross polarization of the gravitational effects. So, I cannot tell you spontaneously what is the experiment. It's a very fresh result, but that is something which does not appear in let's say, gravitational theories which are based on the Lagrange model.
Can you comment on the comparison between string theory and loop quantum gravity? Another hour. Okay.
Okay, so I guess the one, we spoke earlier about sociology. So certainly there's very different numbers of people involved.
No.
For me personally, okay, it's kind of there's loop quantum gravity. There are some few assumptions which I think here a key assumption is actually that in the end, this exponentiation of the holonomies and so on, which leads to the anomaly I described, which has this area operator, the area variables as being more fundamental. That is one of these things which seems to play an important role here. For string theory, it starts from very different assumptions, and also me personally, I'm not quite sure how to define string theory.
But you don't pretend to fix the dimension, right?
Yeah.
String theory will give you the dimension is 11, or this kind of.
Yeah, also overfitting. So what I mean is that I would say that there are different paradigm changes in string theory, and I'm not sure where to attach myself.
Okay.
So I think in the last years, string theory was very much changing from traditional string theory, like 11-dimensional things, to what's holographic is encoded in entanglement. Geometry is encoded in entanglement, and so on. And we do see some aspects of it, like geometry, a relation between geometry and entanglement. Also holds here that areas are more fundamental, holds also in holography, if you believe in the 4-dimensional space-time. So if you have 4-dimensional space-time, There's the so-called Rui-Taganagi formula, which then would apply to three-dimensional slices. And entanglement would be based on surfaces. So there's this claim would be you reconstruct your geometry from area measurements. So that, and in 3D, again, it's a topological theory. Holography seems to hold. That's why it holds in the strong form people say in 4D. I personally don't know. But it's interesting that there seem to be parallels. And I think one question I have, which I cannot answer to you, is for me how much of which version of the holographic principle holds. Is it a very strong version or is it a weak version? I would say.
Okay, can we check if there are
Yeah,
questions?
there is someone asking a question online. He says, why do you require IRS finiteness? Space may well be infinite. And the second question is, what is the status of obtaining Newtonian gravity in the low curvature limit?
Okay, so it's
Perfect.
infrared finiteness. So here I used infrared and UV very loosely. In fact, one comment is that it was way too loosely, and actually it's not very clear in quantum gravity what is UV and infrared. So what can actually happen is that in these quantum gravity states, you can have a region where it's surrounded by a finite area, but it can have, like if you go deeper, you can measure infinite areas and so on. And then if you try to define this path integral, you have to sum over all these configurations, and that could give you infinities, which you would have to do something about. Right? Could we normalize it away, whatever that means, but then you're possibly doing something which you wanted to resolve in the first place. This finiteness also only applies as long as I'm on a fixed time relation. So if I want to describe really asymptotically flat infinite spaces, I would get like these infinite large, I would need infinitely large, infinitely many building blocks and so on. So I would possibly regain some of these infinities if you want to have these asymptotically flat space.
Second
And the
question?
second question was, what is the status?
Of obtaining Newtonian gravity in the low curvature limit.
Newtonian gravity. Well, I presented this result here of obtaining linearized GR actions, so gravitons, which would be propagating degrees of freedom, which give you Newtonian gravity. So perturbatively, yes.
I'm sold. Are there any other questions? No other questions? Let's thank Bianca again.